What have we here? Blurry thing. Ah, a cube.
Wow. What's the length of the diagonal of the cube?
That's right. These are a bunch of slides that illustrate some aspects of color maps that I talked about a couple times ago. This is a plot in 3D space of a color map. The cube represents the red, green, and blue axes in the color space, and so all the possible combinations of red, green, and blue between 0 and 1 fall in some point within the cube. Now with an 8-bit frame buffer, when you have a color map, that means you have 256 different possible combinations for each of the frame buffer values. And so this is a scatter plot of the values that are in the color map at any point. This is just a linear ramp going from black to white. Black is the lower left-hand corner where they're all 0, and white's the upper right-hand corner where they're all 1s. They're equally spaced in color map value. And if you put a picture on the screen which consisted of a bunch of vertical stripes of frame buffer value 0, and then 1, and then 2 going all the way across up to 255, you get a picture something like this. The idea that we're illustrating here is the idea of gamma correction. If you have equally spaced colors, you get a fairly, most of the left hand of the screen is dark and most of the right hand of the screen is bright, and there's kind of a small gap in between where there's actually some perceptible change in intensity going on. So if you don't do gamma correction, pictures come out looking a lot more contrasty than they ought to. With gamma correction, you can see that the dots on here are no longer equally spaced, they're logarithmically spaced, so they're all kind of gathered together up at the top end, but on the bottom end, you get larger and larger spaces in between them. And this corrects for the electronics and what it does for the signal. And then if you make a color plot of that, you kind of spread the range of gray tones more equally across the screen. And in this case, the intensity changes linearly going from left to right instead of having this abrupt change. Now, of course, when we make photographs off the screen, the film processing somewhat bends the intensities a bit, but the general idea is there. Now, some of the other things that you do with color maps if you're making a color picture is to not put black to white in there, but put black to blue in there. So here's the results of a black to blue color map, and gives you different shades of blue going into black. And so here's a randomly chosen object illustrating the blue color map. And you can see the highlight here looks brighter than the other part of the thing, but it's still bluish colored. And many of the models for doing highlights have to do with determining that the highlight is going to be white instead of blue, and you can figure out the calculations for that. When you don't have an 8-bit, when you don't have a complete full color frame buffer on that, you have to cheat a little bit anyway. And do that by making the color map do something like this, which means it starts out at black, and you can see this bright stripe is our color map values going up to a kind of a medium blue, and about 3/4 of the way up it takes off and starts going off to white, which means that the color looks something like this. It starts out dark, and as the brighter end of the things turn white instead of just light blue. And when you make a picture of a teapot like that, suddenly you have white highlights. This is really totally a kludge, but it makes fairly decent-looking pictures. This is a view of a more colorful color map, which is one that has 16 different colors in it, each of which have 16 different brightness levels. We're looking kind of down the axis of the cube in order to make the scatter plot a little more comprehensible. But basically you have 16 lines radiating from the black corner of the cube. This is actually a slightly different color map. This is eight different colors, but this is roughly the thing that you get here, where you have any of 8 different or 16 different colors that you can pick, and you can make different objects with different colors on them. As long as they don't overlap, and you have to start blending the colors together, you're in good shape here. If they overlap and you're not doing anti-aliasing, you're still in okay shape, because the pixel is either on one object or another. It's a point sample. You get ragged edges, but at least the edges have a reasonable color to them. If you try to start blending these things together, the program has to do various elaborate, bizarre things in order to come out right, and even then you don't really come out quite right, because you don't have, even though you have all the colors for the objects in the color map, you don't have colors for averages between any two pairs of objects in the color map. This is a color map that I used for some of the atomic modeling things, where there's a color in there for gray for carbon and blue for nitrogen and red for oxygen, things like that. And here's a sample, a couple of the objects in DNA, 2 of the nucleotides for that. Now this again is not anti-aliased at all, and so we can get away with making the abrupt transition from one color to the next. The jagged lines in there are fairly apparent, but they're probably better to make jagged lines proper color transitions than to make blurry lines with funny, bizarre things in between the colors. This is a color map that I use mostly for the gorge or flyby things. It's got a white on one end and gets into an orangish and reddish color on the other end. It's the sort of thing that you get with that, where you have a gray object, which is a spacecraft, in the foreground, and then a yellowish or reddish object in the background. And where they overlap, you get a fairly decent blending, because white and orange, when blended together, gives you kind of a whitish orange.
Was there anti-aliasing in that movie?
This was, yeah. We'll show a little bit of that in a second. And here's a color map for Uranus. Had one value in there for the gold antenna on the spacecraft. It turned out that if the spacecraft got in front of Uranus, it looked weird because the gold and the green kind of made jagged edges, and so I made the antenna be gray, so that would blend in with the green properly. When you have only 8 bits to work with, you have to play games like that.
How do you determine the intensity on something like that? When you have this, is that accurate to something?
The intensity on which?
Or the greens, the variations of the green?
The particular surface map in this case was drawn by an artist. It's a hypothetical map of what the clouds on Uranus might look like.
Or you just imitated it?
Yeah. The mapping process itself is what we're going to get to in a couple of minutes.
Were the planets quadrics? Were they really spheres?
Planets were really spheres, well, ellipsoids. The algorithm which I talked about earlier on drawing pictures of spheres was substantially what I was using in order to make these pictures. Solving a quadratic equation, taking the square root basically at each point on the screen. This is sort of a bizarre color map. What does this mean? I forget. Anyway. The next sequence shows some experiments in dithering. This is the original image. This is 255, 0 to 255, a full 8-bit resolution, just a black and white image, to show what the picture is we're starting out with. This is kind of the ideal picture if you have a full resolution display device. This is a picture with a dither pattern applied to it. This is an ordered dither where you have a constant number for each pixel on the screen, and if it's greater than that threshold value, then you color it white. If it's less than the threshold value, you color it black. So this is a 1 bit per pixel picture, and a somewhat magnified version of it, so you can see the dithering pattern a little bit more apparently. The ordered dither process gives you these little star-shaped sorts of patterns in there. The idea being, though, that if you kind of squint a little bit and the pixels blur together, you get an approximation of the red shade or gray. So this is the sort of patterns you get with ordered dither. This is what I call basic dither, which I believe is the right term for when you use the magic square for the dither patterns. And you get the same general idea here. Magnify that a bit. The little patterns that you get a little bit different. They kind of look like chicken feet, but again, if you back off from that a bit, it gives you the proper gray sense. This is a halftone newsprint sort of thing, which tends to make larger blobs, but sometimes these larger blobs are less objectionable. It's a simulation, roughly, of a halftoning process, where I said before that you've got this kind of spiral of thresholds that goes out in a 4x4 matrix and then kind of goes in on the next 4x4 matrix next to it. So you get larger, smaller 4x4 blobs for this, and trying to merge them together. And sometimes it's remarkable that this looks like anything at all because the macro pixel size is so large compared to the original image. But to some extent we're used to seeing these sorts of things because looking at newspapers. Now, the previous pictures have all been 1 bit per pixel, so it's been either on or off. The dithering process really works well if you have more than 1 bit per pixel, but maybe not quite enough. Yeah.
You didn't show any minimum average error picture?
I don't have any of those yet. This is an example of the dithering process applied to a 3-bit per pixel picture. If you just take the picture and you threshold, like this is 8 different intensity levels, this is what you get, all these contours and so forth. If you do the dithering process on that, where for a particular spot on the screen you're deciding whether to color it in this light gray or this somewhat darker gray, so you're deciding back and forth between the two closest intensity values based on the kind of the fractional part of the intensity once it's been scaled up. Get a picture like this. This is a dithered picture, 3 bits per pixel, which looks fairly decent. And even from the middle or the back of the room, you probably wouldn't be able to distinguish it from the original picture. If you zoom in on it, you can start seeing a little bit of the graininess that's there. But it's not bad. So the question is, why do you need more than 8 bits per pixel if you can do this good with, why do you need more than 3 bits per pixel if you can do this good? And one of the answers to that is the fact that this looks real fine when the picture is front lit, and the brightest part of the image is right here, and the difference between one threshold value and the other is not too great. But on the darker side, like if you get down around the outside edge of the thing, the difference between one spot and the next on in the color map, the difference between the brightness of two successive values is a lot greater if you have a linearly spaced quantization in your color map. And so darker things tend to look much more awful. You'll see this show up. I'm going to show the Saturn movie again and point out a few of the effects of that. The space pictures are all dithered in order to maximize the effort, maximize the color resolution that we can get with the 8 bits. But it shows up on the dark parts of the thing, typically the night sides. One of the things that you can do even much better than this, which I haven't actually tried, is to change the way that you quantize the picture. Instead of having equally spaced steps in intensity that you chop the thing up to, if you have equally spaced logarithmic steps in intensity, that is, you take an intensity that you want, and you take the logarithm of that, and then you pack that into as many bits as you've got. And then part of the color map process does the gamma correction and does the translation into the linear color range, and also takes the anti-log of that as well to translate it back into intensities again. What you get is the steps in the color map will be farther apart on the bright end, but they'll be closer together on the dark end, which means the places where you're looking at the equal, the ratios of the intensities, where you're more sensitive to that, there'll be more spacing of color values there than there was when they were all equally spaced in the bright end. Yeah.
So you're saying if you get stuck with a system that only has, say, 3 bits per pixel, that you might want to have some way of spacing those out other than evenly.
Right. Yeah. This should be able to do a lot better pictures. I haven't just never gotten around to trying it myself. It's certainly a worthwhile exercise to try. In a certain sense, this has been a theoretical thing that everybody who deals with theory of this says, yeah, this is obviously the way to do it, but I don't know if anybody's really done it. There might be some technical problems, but most people have 8 bits per pixel per color by now. 8-bit frame buffers are cheap enough, so you may as well get a 24-bit frame buffer if you're going to do fancy shaded graphics like this. So there hasn't been a need for it, but for people who only have 8 bits, you can try do logarithmic quantization of the thing instead of linear quantization. Here's an example of one of the space pictures. This is the Voyager 2 going by Europa. Now, from the places where you're sitting, this might look like a fairly decent picture. I can see the phosphor dots from the screen at this point where I'm standing. They sort of show up. But you can see, fairly smooth shading in the spacecraft, and the lines along here, look like straight lines. They're maybe a little bit ripply, but here's a magnified version of that. And it looks real awful. It's kind of surprising how ratty these things look like up close. And part of the art to this thing is adding enough crap to the thing so that even though it looks crummy up close, when you shrink it back down and your eye blurs things together, things happen properly. The rattiness of this thing is caused by two things interacting. One is the dithering pattern. You can see the little checkerboard patterns all over the place here. And the other one is the anti-aliasing, which blurs things out, where like this area over here is a straight line of a very thin boom sticking out, and it's been kind of blurred back and forth across the line of the pixels. And up close, you can see it looks like a bunch of more or less randomly colored dots. And similarly, the spacecraft, this thing here is actually a conical-shaped cover for one of the instruments, and it's brighter on this side than on the other side, but at this resolution it looks like a bunch of funny dots. But when you shrink it back again, you can see right there, it looks like a little piece of a cylindrical something. So it's interesting to see how the eye can be fooled into thinking there's resolution there that there actually isn't. Right there, it looks like a little piece of a cylindrical something. So it's interesting to see how the eye can be fooled into thinking there's resolution there that there actually isn't.
Wouldn't you be able to tell more directly if you looked at that resolution but saw it blurred, such as the eye would perceive?
Ideally, if you interpolated the pixel values or the intensity values from one to the next, you'd get a better impression of what this is than looking at things replicated into ideally square boxes.
What kind of anti-aliasing did you do here?
Most of the space movies used lots of cheap, sleazy tricks to do the anti-aliasing, partly because of the time I had to write the code and because you wanted the things to run in a reasonable amount of time and so forth. The spacecraft, or generally the polygon drawing program which I use, does anti-aliasing by computing the picture, point sampling it at 2000 by 2000 resolution, and then averaging down every 4 by 4 box into one pixel. So in a sense, the filtering function that's being used there is not even a box window. It's not a Fourier window, it's called. It's a bunch of spikes that are equally spaced in a 4 by 4 grid across the pixel, where it point samples the things in 16 areas in between that. That's real simple to implement, and it's not spectacularly fast because you have to. It's like computing 16 pictures instead of one, in a sense. But it's something I tossed into the program real quick at the last minute in order to get the thing to go, and never gotten around to fixing it yet.
Could you have the guy turn off those monitors?
Have the guy turn off the monitors. I can maybe tune down the volume on these things. There we go. All I have to do is touch the buttons and the monitors turn on. Cute. Yes?
What other cheap and sleazy tricks do you know for anti-aliasing?
Basically, every anti-aliasing algorithm is a cheap and sleazy trick. If you look at the mathematical details of it, what you really have to do in order to do anti-aliasing right, you'll just get totally grossed out by the whole thing. You just won't even want to deal with it. Everything always winds up being some approximation to the real thing. The image of the disk of the planet, for example, was again point sample, except right at the edges, just on the left and the right edges of the thing, it can calculate fairly easily exactly where the silhouette outline of the thing intersects the scan line, which is some fractional distance between the pixels. And so it colors in the inside pixel, whatever color it figures out. And then the one just to the left of it, the one that's just outside, it colors in using the average of black space with the color inside the disk with a ratio based on the fractional distance that the actual edge is between the two pixels.
That's the same idea as the Brazenhams with the error
More or less, yeah. The only trouble with this thing is that it works okay only for the left and right edges. The top and the bottom edges it doesn't do particularly good on, because on those you've got to go out more than one pixel. It's a whole range of pixels. But again, this is something that was easy to toss in real quick at the last minute in order to just fuzz the thing up a little bit. For planets it works better because the left and right edges are where the brightest things is. Near the poles are where the day and night side is, and so it's not quite so important because you're dark there anyway. Yeah.
Are there two booms coming out to the left?
Yeah, this thing here is one long skinny boom, this is one long skinny boom, and this is another bunch of long skinny booms.
Yeah, that's what I was.
It's 3 prongs kind of sticking out of the spacecraft. I was sort of worried when I saw the design of this thing, because there's all sorts of long skinny booms in this spacecraft. These are the worst things you want to draw on a raster display, because they're the ones that are going to come around and bite you. And in fact, the booms look kind of flaky if you get very far away from them. If you get reasonably close, then they're okay. And in the mathematical model, the radius of these things is 3 or 4 times what the actual radius is on the spacecraft in order to make these things fat enough so they don't get too hacked up with the aliasing. Okay, texture mapping. Texture mapping in concept is really fairly trivial. It's the basic idea is that you have some object defined as a bicubic surface. This is just a description or plot of the mesh of the control points for the teapot. And you have x and y and z being functions of u and v. Hold u constant and move v back and forth, and it'll trace out one curve. You hold v constant and move u back and forth, it'll trace out another curve. In addition to making x, y, and z be functions of these u and v, let's make other properties of the object be functions of u and v, like the color. That is, once you come up with a particular pixel on the screen, and you know that you want to shade that in, and you can calculate the normal vector, you know the u and the v, the parametric values on the patch for that point. So instead of just using some constant brightness factor for the surface, you plug the u and v into some other color definition function, and you use that value. Color definition functions then can be defined in any of several ways. Here's just a blank teapot to serve as reference here. And here's one possible color definition function. Fairly simple to generate algorithmically. Basically, you multiply the u and the v by 8, take the fractional part, and if it's less than a quarter, you make it white. If it's greater than a quarter, you make it gray. So you make this get this replicating pattern of checkerboards.
What are those lines down the
The
center?
line down the center was an artifact of the imaging process, shall we say. As it happens, only the left quarter of this thing was the actual pattern, and I wanted to make the whole screen fill up with it, so I made 4 replications of it, and program, for some reason, decided to put a gray stripe in between them. So this is basically table-driven. This particular program actually had a 4x4 table, which it looked into, and so you could make little 4x4 replicated patterns going all over the surface.
Excuse me, it's interesting you get this optical illusion of a dot between each of the
That's a
squares.
classic optical illusion, as a matter of fact. I forget the name of it, Ponzo or
If you look at any one intersection, you don't see it.
if you look kind of, generally it looks like there's a dark dot in the intersection of these things, and it again has something to do with retinal fatigue and what do they call the thing? Lateral inhibition within the retina. Well, far out, you see all sorts of things, yes. Here's a teapot with checkerboards on it, right? So in a sense, this pattern sort of shows off the parametric lines again. You can see them radiating out from the top and so forth. So this is very similar to the line drawing picture we did before, where we just have gray lines and white lines going across the patterns. Here's maybe a more interesting picture. This was a digitized photograph. I have no idea who this is. People always ask me who the girl is in the photograph. I got the database from a friend of mine at Michigan, who got it from a friend of his at MIT, who, 8 levels back. Whenever you get yourself digitized, you're going to show up in bizarre places from now on. It turned out that I had this laying around for whatever purpose. This is an interesting picture to look at. This is 256 by 256. This is a really good-looking picture. I mean, you don't see jaggies, you don't see, not obvious aliasing. You can see little horizontal streaks, which are an artifact of the process of making the image scanning out. But this shows you how good you can do with even a low-resolution picture. It's full intensity resolution, 256 levels of intensity, but it's really only 256 elements across. And you look at the wispy hair and the lines in here and the eyebrows and so forth, and they all look really nice. And one of these days we'll be able to do this. This is a lot of parallel processing in the anti-aliasing going in here. But you can use this thing as a texture pattern. It's a 256 by 256 picture. It's just used table lookup, basically. You take the u and the v value, multiply it by 256, and that'll give you an index into the table. And the integer part gives you the pixel values you want to pick out, and the fractional part gives you kind of the distance between that and the next one. So typically you do like bilinear interpolation, and it'll make a smooth sampling of this thing. And here we have places on a teapot. So the T-like pattern. Each square is one patch. So this is sort of good to show you where the patches are too in the design of this thing. There are 4 patches going around the surface of revolution axis of this thing. 3 patches going from the bottom to the top. There's one kind of small one going on the lip, one for the top of the lid, one for the knob, and various of them for the handle and the spout. And you can do interesting things like this. This is, you can of course take weird patches and bend them all over the place and do bizarre things. This is an attempt to do something similar to what artists got into 100, 150 years ago, anamorphic images, which is they paint something in the manner in which, if you look at it in a cylindrical mirror or some odd-shaped mirror reflection, it'll reconstruct itself back in the original picture. The idea of this thing is if you had a print of this thing and you laid it down on a table and put a cylindrical mirror right about here and looked in the mirror, you'd get to see the face again. And it's approximately correct. But the patch itself is just one patch with one degenerate edge. This is one edge of the top here. This is another edge, the whole circle going down there. One edge going in like that. And then the fourth edge of the patch is one point basically in the center. So this is roughly a polar plot thing. You have one set of parametric lines going radially out from the top edge, another set of parametric lines going in concentric circles, approximately circles.
You ever wondered if this woman is going to come back someday and sue for this kind of thing?
Yeah. I haven't worried about it too much. If she claims she looks like this, then she's going to have trouble with herself. Okay, here's a pattern you might more likely see on a teapot, perhaps. This was painted in with a painting program. Basically, once you have the mechanism involved for taking any picture and twisting it across the surface of the patch, then you can paint the thing in with a painting program, scan it in photographically, any number of ways of generating the patterns. Here's the teapot with flowers on. This is kind of a random streaky pattern that was put together with, actually it was a 2D Fourier transfer program I had, which you paint the Fourier transform on the screen, and then it would take a 2D Fourier transform of that thing and come up with odd streaks, and then you put that on there, and you get sort of milk glass effect.
How can you get this joining them?
Well, if you're careful, see, this picture, this texture pattern happens to be cyclic, and that, in other words, if you look at the right edge of it, it's the same as the left edge. That is, and as a matter of fact, the problem with it, which I guess maybe Lauren Carpenter alluded to a couple times ago, in that if you have several different patches end to end in your object, you have to make sure the texture patterns line up and match up end to end from one to the next. With the face picture you saw, that didn't happen. You can see obvious seams in between them. This particular pattern here is cyclic, both left to right and up to down, which is easy to do with Fourier synthesis. And so when you glue a thing together, you get a smooth boundary in between them. But you can sort of see maybe something a little fishy going on here.
To what do you attribute the black squares at the top there? Is that an artifact of...
This here?
Yeah.
That's the aliasing of the lip, basically. This is a point sample picture. What happens is, when you have something that's highly curved like that and you point sample it, one of these black squares is right on the edge where the thing is kind of edge onto the eye, and so the intensity of that is black, even though that geometrically only shows up for a very small space on the picture. That happened to be the sample that you stepped on, and so that is used for the whole pixel there. The size of these black images, you can black dots are 1 pixel on the thing. Here's a bunch of other strange things that were done at New York Tech. This is a texture pattern drawn by Lance Williams, mapped onto a cream pitcher. The teapot and the cream pitcher and most of these silverware sorts of things were originally designed by Martin Newell for his thesis. So he had the database laying around. I scrounged it up to use to run through the programs I had. Frogs on the teapot. Yeah, you should, at this point you can start imagining some of the bookkeeping problems necessary in doing texture mapping, where you want to have a different pattern for the different patches, or you want to have different replications of the thing. There's parameters within these programs to replicate it some number of times, you always want to put patterns where the pattern comes out backwards or rotated from what you wanted to because you had the parametric lines going in the opposite direction than you thought you had. So you need a little kind of manipulation program. You make a picture and it's rotated the wrong way. So you go into your texture pattern, you transpose the matrix, and then you look at a thing and you find it's upside down. So you go in your texture manipulation program and you rotate the thing 180 degrees. And so there's a lot of iteration like that to do. So it's another example of one of those things that you can sit down mathematically and figure out, well, U increases in this direction, V increases in that direction, and the image goes X and Y like that. You can probably figure it out, but you only, again, wind up with a 50-50 chance of getting it right. So you're going to have to do some editing after the fact anyway. This is an example of some of the errors that crop up if you're not too careful about how you calculate the parametric values. This is was done using the Scanline algorithm, the speeded up version of it, which takes some sample points across the scan line and just linearly interpolates the object and the U and V values in between. You get obvious linear edges here where, of course, the thing is supposed to go in a smooth curve down across the saddle point. You get funny little crinkles and so forth. So some of the speed ups to the algorithm work okay as long as you're not doing texture mapping, but you have to be a little bit more careful with that. Now, aids to this, you can start getting elaborate, and instead of linearly interpolating the U and V across one scan line, you can do a cubic spline interpolation to, figure out the tangent to the thing at both ends, and shovel more and more mathematical complexity in it. Basically, the punchline here is that in order to do it mathematically correct, it's harder and slower, and in order to do it quick, you run the risk of getting mistakes in the picture. Here's an example of, space pictures. This is texture mapping on a sphere. The texture mapping on arbitrary bicubic surfaces is, of course, a lot more general, but it's slower because it's restricted to the bicubic surface algorithms. For spheres, you can do a lot faster algorithm. In this case, it figures out, using the quadratic surface algorithm for a particular pixel, what's visible, and so you now have the coordinates of this pixel in what you call unit sphere space, the canonical measuring space of in viewing space, which is the space sitting out in front of the screen. You have to multiply that by the inverse of the viewing transformation in order to get it into unit sphere space. Then you take a couple of arctangents to convert that into latitude and longitude space, and use that to look up in the texture map. Arctangents can be done a lot more quickly with some simple binary search, subdivide, table lookup processes, but they still soak up some time. Now, yeah.
Question about the mechanism of the actual texture mapping. You just can't look up in the parameterized space and grab the pixel value. What you do is that in the parameterized space, you're going to get some sort of, you're going to get the pixel as it's inversely mapped. And what you got to do is you got to average the area that's inside of that.
Yeah, that's what we're going to get into in a moment.
Okay.
As a matter of fact. Let me say a few things also about the bookkeeping process of keeping track of these texture maps. I'm familiar primarily with what I've done and what New York Tech has done, which have been in somewhat different directions. New York Tech has a lot of frame buffers, and they wrote most of their programs to operate using multiple frame buffers, where you have the thing that you use 3 frame buffers to store the texture pattern, red, green, and blue color separations. So you have a 512 by 512 texture pattern. 3 frame buffers for the output picture, which is where you're going to display the image, and a few other frame buffers for object tags and whatnot. And so you generate this picture using essentially direct access to the texture map using the frame buffer. The frame buffer is just like a large memory, automatically accessed as a Fortran array, because you have 2 registers, one for X and Y, and the 3rd register gives you the Z or the intensity value there. I have not had 3 frame buffers or 10 frame buffers at my disposal, so I do these things mostly paging them on and off of a disk, which is a bit slower because the disk access is slower, and you have to do a little bit more bookkeeping to keep track of exactly where on the disk you want for a particular XY coordinate in the texture map. But it's substantially more general in that you can use the thing any time because the disk is a common device. It's always there, you can always page on it. They ran into problems at New York Tech where some people wanted to use these 10 frame buffer algorithms to draw a particular picture, and it draws up in 5 minutes once you've got the frame buffers, but somebody's using frame buffer A for painting, and somebody's using frame buffer B for recording things and so forth. So you have to wait around 2 or 3 days until everybody goes home and goes on vacation before all the frame buffers are free and you can use them. And sometimes it seemed to me silly to have a program that runs in 5 minutes if you have to wait 2 days to run it. Much better to have a program that takes 10 minutes to run, but you can do it any time, which is the case if you have page the thing on and off a disk. Ultimately, the answer to this thing is to have the mechanism within your system support to have what amounts to virtual frame buffers. That is, at runtime, you can either hook up the I/O to a bunch of real frame buffers, in which case the data access of it is real quick, or you can optionally have the thing hook up to some virtual simulated frame buffers on a disk where the system code takes care of paging in and out the different parts of the image for you, and so you can do it in either mode when you want to. Now, when you're doing this thing on a disk, there's also some probably what amounts to classic problems in data accessing and localization of the information. The initial version of this program used to store out each scan line of this texture pattern on one record on the disk, basically. The texture pattern is 512 across by 256 up and down. The 512 goes across the equator, around the equator once. Top edge is the North Pole, bottom edge is the South Pole. So 256 samples from the North to the South Pole. So whenever you look for a picture, it's got a set of maybe 8 or 10 buffers and does a simulated virtual memory scheme, least recently used and all that sort of stuff. Sees if that particular record is in the buffer already, and if not, finds the one that's oldest and replaces it with paging in off the disk and so forth. That doesn't work particularly well for things that are stored in that way, because a whole bunch of horizontal strips means that if you scan across, say, the North Pole of the object, the accessing pattern across the pattern in the frame buffer goes kind of up like this and then down again. And so you have to page every scan line in and every scan line out again as you go across the thing. Recently, I've gotten the thing into a little box-like structure where each record on the disk stores a 64 by 64, I think it is, pixel region on the disk, and you page those things in blocks. And so you have a lot more locality of access, where if you have room for maybe 8 or 10 of these things, square block buffers in real memory, then you're more likely to have the whole working set, as it were, in from one scan line to the next, and you don't have to thrash on the disk so much. And this speeds up the program an enormous amount. Yeah.
If one is working in a virtual memory system, all one has to do is make sure the arrays are set up right to begin with, and they should get all the rest of that automatically.
Virtual memory systems operate easier for the programmer, certainly, because you don't have to do this thing manually. You just say, okay, haul this whole thing into virtual memory, and this is an array. Well, you can.
No, I mean, you have to cut up the array.
Right, you have to cut up the. That's exactly the point. You have to cut up the array a little bit more intelligently. You can't totally depend on the virtual memory to save you. You have to cut up the array in roughly the same way. The classic example of virtual memory getting killed is to take a 4,000 by 4,000 array and try to initialize it to zeros, going the wrong direction down the array, right? So you have to have a page fault on every element. You run up against the same sort of thing here. So you need to glob things together into little boxes instead of horizontal strips. The globbing together in boxes comes up even more in other aspects of this, which we'll get to in a minute, that have to do with anti-aliasing. Speaking of which, one of the things that happens with texture mapping, again, is aliasing, as anything else shows up with when you're dealing with sampled images like this. This is an example of the teapot made using point sampling of the texture pattern. That is, it comes up with a unity value, indexes in the table, and just takes the nearest pixel on the table to that thing. Now, it might not hit you over the head that there's a lot of jaggies in this thing, and so we have a few zooming in on it versions of the picture. And you can start seeing, especially near the lid on the teapot and the handle, where the texture pattern all kind of converges together in one point. What we've got is one pixel covers a rather large area on the texture map. And so if you point sample it, you're taking a point sample of a fairly large area in the map, and so the aliasing problem is a lot more severe with texture mapping. And it hits you a lot sooner and a lot harder than it does in just working with edges of things. Basically what you have is this sort of situation. You've got the texture map on the left, the U and the V area, and you've got the picture on the screen on the right, X and Y axes. Each spot on the screen is one pixel dot. When you have this patch on the right-hand side that you're drawing, each pixel on the patch really is supposed to be an area average version of generally surrounding plus or minus 1 pixel size here. So this entire box around this 1 pixel contributes to the intensity of that pixel. Now, if you inverse map that into the texture map, you've got this somewhat bent quadrilateral here, and so you need to take an average of this entire area on the UV and the texture map space in order to really accurately represent the thing in the screen without getting a lot of aliasing. Now, the outside rectangular regions of this box can be really bizarre back in the U and V space. If the patch crinkles around in strange ways, the exact shape of this thing can be something really unpleasant. So this is another aspect of the fact that really doing anti-aliasing right would involve a lot of gross geometric calculations to bend this thing around the proper way and properly weight the average of all of the samples of the texture map. Generally, again, you do some approximation by saying, let's take the square or the parallelogram that's closest to this thing. You can generally take just the U and the V derivative of the patch, which you have to calculate anyway for the normal vectors, and transform it back into the space and get a squarish region in here, which you can sample with an averaging process.
Is that what was used on the images we saw earlier?
A lot of the images were just point samples, but the next couple of images show that. First, I want to show a few sampling filters here, since I've got happen to have them in the collection. This is a windowing function or an averaging function. The idea being here that the gray area represents the screen, and this box here represents the weighting function that you're going to weight the averages with. And so this is a square wave box filter, Fourier window, whatever you want to call it, which means that just all the pixels within plus or minus 1 pixel distance of the center get equal weights. And this works better than doing nothing, but not as good as some of the other ones. This is it's called a Bartlett window, which is kind of the next higher order approximation of that. The first one does just constant function approximation of things. This is doing linear interpolation, basically. You have the pixel itself is in the center, and the weighting function drops off to 0 as you get plus or minus 1 pixel away from the center. And so if you imagine the weighting function applied by the altitude of this light-colored triangle above the brown background here, that's the weighting function that's applied at each part. And this gives you a much better average, better picture, because it's doing a better job of getting rid of the high frequencies which you can't represent, but not throwing away the high frequencies that you can. That's basically the criterion in doing anti-aliasing. The ideally theoretically correct function is this, which is sine x over x in both the x direction and the y direction. It's the product of sine x over x times sine y over y, basically. And it has about the same shape nearby as the tent filter that we had in the previous slide. And this square region here represents plus or minus 1 pixel surrounding the image on the screen. So the size of the side of this thing is 2 pixels. But it kind of ripples negative, positive in sort of checkerboard fashions. It goes away infinitely far. The ripples get progressively smaller and smaller, but they do go out theoretically to infinity. And so if you want to do proper anti-aliasing, you really have to think about integrating the entire picture out to infinity with smaller and smaller little ripples, which, again, seems like more trouble than it's worth, and it probably is. There's a threshold at which the improvement is not visible to the eye, and you have to kind of come up with some engineering, maybe psychophysical measurements about how accurately you have to do the filtering before you get to the point where the eye is not going to notice the difference anyway. Now, if you do some sort of area averaging to this lid of the teapot, you get something like this. This was done by taking the pixel on the screen, and the derivatives, the U and V derivatives of the texture pattern, mapping them back in the texture space to carve out some area on the texture pattern that you have to average. I believe I used a tent filter on this thing, which is the second order thing, the middle of the 3 filtering functions that I showed. And this gives you a blurrier effect, and as we kind of back off from that, you can see blurry radial lines, but at least they look like radial lines instead of little odd speckles and things that we had in the original picture. We finally back off all the way, and the image, especially up near the lid on the teapot, looks a lot more like radial lines going away from the top. You back up and try to compare this with the original unplayed with picture. Here where you have the lines kind of radiating from the top, there's places where they disappear entirely and they get kind of all hacked up. And even in the original picture, you can probably see some little messiness up here. Let me back this up to the right spot. This is another little demonstration trying to show the difference between doing the averaging before and after sampling, which is a lot of people will say, well, if you have a picture with lots of aliases in it, you just blur it after you've made it. Simple process to do, and that'll kind of get rid of them. And this is, again, theoretically, doesn't work too well, although you can probably, for some images, do some improvement. The idea is, this is a point sampled image of checkerboard pattern on the sphere. That's just point sampled, and then the pixels are replicated into little squares. A little blurry because of the quality of the slide here. If you blur that up after the fact, you get blurrier lines, which look somewhat better than just replicating the square. This is doing linear interpolation between each pixel value, and so the interpolation on the screen is better. The limb of this, the outside edge of this thing, nothing is being done at all, and that was done because it was easier, and also it kind of gives you an idea of the size of the pixels that we're dealing with. This is a magnified version of like a 128 by 128 image. But the lines on here look somewhat better. This next picture is, if I'm getting these things in the right order, yeah. This is an area average picture where the thing was area sampled, but it still uses equally replicating the pixels, and so the boxes are uniform intensity. And here's doing everything right, which is area sampling it and doing interpolation. So the two processes you have to do are doing area sampling to construct the pixel values, and then doing a proper interpolation between one pixel value and the next. You can't just color in an equally colored box for each pixel and have it come out right when you finally come up with the final image. Now, there's one other thing I want to get to. Oh, this thing just likes to jump all over the place, doesn't it? One other thing I want to mention in terms of the anti-aliasing of texture patterns, it has to do with an idea that I believe it was either Ed Catmull or Lance Williams came up with for doing anti-aliasing quicker. And that has to do with the idea that if you have some fairly detailed texture map, maybe 1,000 by 1,000, so that when you zoom in at real close, you're going to get something there instead of a bunch of blur. When you back off from the thing and see the thing real small on the screen, what you wind up doing is having a small area on the screen mapping to a large area in the texture map. So you have to do an averaging process over a lot of pixels within the texture map. It's a lot of summing up to do all the time. And so they had the idea of doing the averaging kind of once before the whole picture. And that is, you store the texture map in several degrees of resolution. You have 1,000 by 1,000 version of it. Then you have one area average 512 by 512 version of it, and the 256 by 256 version of it, 1028 by 128 by 128 version of it. So you store this thing in maybe binary steps of resolution already, and then when you go to draw the picture, you find the area, the size of the box that you're trying to average over the whole picture, and use that to select which of the pre-averaged texture maps to pick the picture element out of. And this lets you not have to sum up so many pixels within the texture map. And they came up with a name for this called MIP mapping. MIP stands for multum in parvo, which is some Latin term for many into one or some such thing. It's a jargon term which this is typically associated with. There are some problems with this, however, in that if you don't do it carefully, you wind up with visible artifacts. This is happening. If you imagine a square, flat plane that's kind of receding into the distance, I wonder if I can maybe draw a diagram on the page here to illustrate that. So I can see. I need to get these monitors turned on so I can see what I'm drawing too. I didn't turn them off. I just touched the box, and the guy in the back saw that I needed to do it, and so he turned them off. Oh, I can see in the back room. If you imagine a, there we go, a perspective image of a patch kind of receding off into the distance. When the thing is up close to you here, you're going to want to sample the thing in the high resolution part of the texture map. And where you go back here, the medium resolution, map. So this might be out of the 1000 by 1000 map. This might be out of the 512 by 512 map. And this might be out of the 256 by 256 part of the map. And if you're not careful, you're going to get kind of an abrupt transition in the texture, or the graininess of the thing from one spot to the next. And so what actually has been done is the approximation of saying that when you come up with a spot on the screen, which is 1 pixel, and you map that back into texture map space, you have to actually do an interpolation between the medium res and the high res texture map in order to get some blending across here, so you don't get an abrupt change in fuzziness of the image from one to the next. Okay, I think we need to stop now for a tape change. And okay. You need to cut off these monitors again here too when you get a chance. Let me show a couple of these films over again that we showed at the beginning. I think I showed both of these at the beginning. So you can sort of see all the mistakes this time that you might not have noticed before.
Right?
What's that?
Digital dust.
Yeah, the film's getting a lot dirtier than I thought it was. Now the stars in here are all point sample stars, which means that they're, each star is a little 3 by 3 pixel area down there with linearly interpolating in between. You might be able to see a little checkerboard pattern on this, which is the quantization. You can see the intensity of the polygons abruptly changes from one to the next. That's because I was doing something really stupid by throwing away the intensity resolution before I did the dithering, which I'm trying to fix right now.
Is this the one where you cut pieces?
This is the one where the 2 missing frames, because the mathematics of the sphere drawing blows up, and I'll try to point out to you where those are if they're not obvious by now. Coming along pretty soon.
Yeah.
That was not it. That was a dark frame because the camera glitched. We might have already passed it. Not so obvious as I thought it was.
Really?
There, that was it there, I think, where the thing seemed to jump. Now you can see this little boiling effect that goes on the night side. That's where you're having dithering on a low intensity picture where it's not showing up as well as it should. And shortly we should get another jerk in here where the parabolic effect happens on the way out. There. That's just it, I think. So it's sort of interesting to see how much you can get away with sometimes, because a lot of these things would not be obvious if something wasn't pointing out. See, right there is where it glitched. Although sometimes you have the reverse effect where things are worse than you'd hoped. A lot of the jerkiness you saw during the pan there was because there was no motion blur in this, where each picture was exactly crisply calculated, and even though the camera was moving fairly fast, you can see the stars kind of turn into 2 stars as they go by, right? That's because of the double shuttering effect of the projector, where each picture is actually flashed on the screen twice. So you get 48 flashes per second, which is merges together into a perceptual constant image, but you only have 24 different pictures per second. So you get start here, twice here, twice here, twice here, and twice there. Even though your eye is tracking it smoothly across, the image on the retina is kind of jumping back and forth between 2 spots.
Peter Blunt.
It's my brother. More color wedges. You know, we have huge piles of color wedges on all these things to go through and measure with the densitometer to get the color response of the film. Color boxes and whatnot. Let's switch to the next film then.
Another problem I've noticed is that when you pan, transition from panning to not panning is too abrupt.
Yeah.
Slow down.
Most things that you want to do for moving within a movie is to do eases on things. You don't start abruptly, you don't stop abruptly. You start up slowly and get to a maximum speed and then slow down slowly. That's actually done on this thing, but the function I'm using probably just isn't smooth enough. It's doing a cubic spline interpolation between one endpoint and the next, but as it happens in the business that I know, most people who do this use exponential functions instead of cubic splines. And so things start up a lot more slowly and they slow down a lot more slowly. but it's something that's fairly simple to do with computers. Most of the camera track motion things, this is a big thing with them, is talking about the exponent of the curve on each end and how to make them match up so that they're continuous from one motion to the next and so forth. It's the sort of thing that you have to tune a little bit for aesthetic purposes. To 5, my goodness. One of the things that I kind of realized that going through what I needed to talk to today is how much stuff we haven't gotten to. We're just kind of through all the basic stuff. We're just getting to the point where we can start talking about interesting things now. Turns over. Oh, well.
Next quarter.
2 years from now, they'll be going to semesters. So.
The seminar. This is the other Saturn flyby movie. You can see a little double framing go on with the letters going off my distance as well. Looks like those things turn into 3 dots, some of them. This might be a 3-shutter projector, I don't know. Certain parts of this thing are single frame. Most of them are single frame. Some of them are double framed where the motion doesn't go too fast. You can kind of get away with that and only have to calculate half as many pictures. But it looks more jerky if things are moving fast.
Polygons on the edge.
You can see the polygons on here. There's something like 30 polygons going around the circumference of the dish of the antenna, which was as many as I thought I could get away with within the program. There's a limit to how many polygons the program can hold. It's a PDP-11, so it's got to be able to sort all the polygons in Y order at some point or another. That particular pan there was double frame, which that's the one thing I didn't get a chance to single frame. This is Titan. Now, I see an interesting effect here, a sort of fluttering effect in the night side, and that was because this was filmed off of a TV monitor. And there were hum bars in the TV monitor, which means a 60-cycle noise getting in there. If you watch the screen, you can see very slowly these kind of light and dark bands move up the screen. Now, since I was doing single-frame animation on this thing, clicking the shutter every 6 seconds, the hum bars were kind of at random points on each frame, and so you get this hum bars jumping all over randomly on that.
That boiling at the top is
This is the aliasing that happens at the North Pole because it's not blurring it properly, but on the left and right edges of the thing, it looks a lot better. You can also see some interesting glimmering going on in the dark edge of the rings there, which is more dithering patterns. Now here, the boiling on the night side of this thing is fairly noticeable.
Is that dithering?
This is the dithering, yeah. The night side, artificial scale up the night side on this thing is a lot less than on the previous movie. I made the night side darker. Normally it would be dead black, but I just made it darker gray on this, and so the effect of dithering is a lot worse. Now, the anti-aliasing along the booms on this thing work fairly good for this scene because they're just big enough to blur out properly, and so you don't see a lot of ants crawling around on there. So we kind of lucked out on that one. But you can see it when it gets darker because we're probably getting more into the intensity resolution problems than anything else. You can see, some more obvious checkerboard patterns in there. I think what I plan on doing in the next movie, we have a full-color frame buffer, but I don't think I have time to get all the software going on it. So I'm going to try doing it at 64 colors, 64 intensities and four hues, which packs the intensity a little bit better way to what we need.
Those look like motion blur.
Now, the streaks on there were motion blurred. The program calculates out for each frame where the thing was in the previous frame and where it's going to be on the next frame. It makes this dark to light streak in between. And so the overlapping streaks didn't give you the sort of doubling up effect because they were moving so fast. I decided to try that. The geometry of it was simple enough so it was a fairly simple experiment to make.
Shadows for the meteors are constant?
The shadows of the craters were painted in by hand. The artist drew just an image knowing which direction the sun was coming from in order to make that come out. You could do kind of before the fact texture mapping on that, but get to that in a minute.
On the rings in the dark, you can see...
Yeah, you can see more checkerboards down here in the shadow of the rings too. Any place that's dark tends to get obvious with the dithering.
You could see the star through the boom as the boom went through.
Yeah, you can.
Well, there's gaps in there. The boom itself is made of a whole bunch of parallel tubes, so it's not a solid object.
some of these artifacts won't show up if they're shown on TV.
That's basically it. TV tends to smear everything, and so you can get away with more. Watch the intensity of the polygons as they go around here. You can see funny things happening, which is because the intensity quantization was done before the dithering happened. In the transfer of the data from one program to the next, the resolution was thrown away by accident, which is too bad. That's something, again, I'm endeavoring to fix up for this next one. A lot of these programs, when you go back and look at them, they turn out to be, unfortunately,
Are you
crummy.
trying to borrow the texture maps from the actual photographs of
Yeah.
the remake?
Right.
Oh, great.
That's what I did between the Voyager 1 and 2 flyby on Jupiter, and I had some interesting ideas on how to do the texturing on the Saturn moons, which I hope will work out properly.
What's the next movie?
Voyager 2, going by Saturn, which happens in August, which is the thing that we're tooling up for right now. Okay, if we can switch back to the slide projector. In 3 minutes, I'm going to tell all about bump mapping. So far, we've done texture mapping like this, which is intensity changing across the surface. One of the things I want to do is try to simulate wrinkles in crumpled up surfaces. And you can do that by taking a photograph of a wrinkled surface and mapping that on the thing. That doesn't really work right because the lighting direction from where the photograph was taken is never the same as the lighting direction for you to resynthesize an image. So the idea that I came up with was to do something different. Instead of changing the intensity of the thing, we'll change the normal direction of the surface that we use to calculate the light. If you look at some wrinkly surface, most of the intensity changes are because the surface is tilted in a slightly different direction than the average of the whole thing. So if you imagine this is a cross-section of the whole surface with all the normal vectors sticking out. This is a texture pattern that we're going to superimpose on top of that with ripples as a function of the parametric direction u, say. And so the final surface is going to look something like that. So when I shade a picture of it, you recalculate the normal vector, which is perpendicular to the perturbed direction of the surface. And so you have the normal vector tipping back and forth in different ways as you do that. And these are some pictures of historical interest. This is the very first thing I tried to do just to see if this is going to work at all. And basically what I did was take a value in the texture pattern and just add it to the x component of the normal vector, and then renormalize, just to see what would happen if you nudge the normal vector around. A couple of different pictures of this. And they were encouraging because they look like something that has, in this case, basket weave on it. It's just a photograph of a basket weave pattern. The intensity of that thing is used to move the x direction of the normal vector left or right. But it looked convincing enough to try to get into mathematics, which is a little bit, takes a lot of partial derivatives and all that sort of nonsense.
What kind of lighting model gave you the blue highlights on the edges?
Well, the blue highlights are an artifact of the problem with Catmull's algorithm for doing surfaces. The idea was that this algorithm was done for doing Nelson-Max's inverting sphere thing, which has blue on the inside and red on the outside. And along the steroid outline, there's a lot of confusion as to which side is pointing out. And so sometimes it made a wrong decision and said, this is the inside part of the sphere, so I'll color it blue, instead of the outside of the sphere, so I'll color it red. So these look something like that. When the thing was finally working properly, this is an example of using the same checkerboard pattern that I put on the teapot for light and dark things, but this is just done on a flat patch. Slightly different thing, the same thing, where it really looks like wrinkles and bumps, even though this is one patch and it's perfectly flat just with the corner bent back. You can see the wrinkles going on here. This is a hand-drawn pattern. When you draw these things in now, you have to realize that you're doing a slightly different thing. You're molding like making a bas relief instead of bright and dark patches. Wherever the thing is uniform color, it's going to be smooth. Where it changes from light to dark or dark to light is where the normal vector is going to tip back. And so this is like the elevation of the surface away from its rest position. So you make a picture, just drawing this thing. This is a line drawing plot, an isomorphic plot of the intensities. This is kind of the dents that are going to be superimposed into the surface. And so if you make a picture of that, you get a strawberry-like effect. The seeds are upside down. This is one of those cases where they came out sideways, and I flipped it, and then they came out inside out, and I flipped it, and I turned it around. This thing, after about 5 tries, I said, this is as close as I'm going to get. And so seeds are upside down. Zoom in on it a little bit, and you can see the effect of this thing in the highlights is what makes it most dramatic, because it really accentuates what's going on with the normal vectors changing. But the surface itself is modeled as a perfectly smooth surface of revolution.
It still looks like a ceramic strawberry, however.
Yeah, there's the lighting models in here are not ideal. Good enough to get a thesis, but bunch of random streaks and wrinkles, which give you this sort of effect, which in an attempt to...
Fit together on all edges?
Yeah. This pattern was done so that they, again, it's cyclic and it wraps around on itself from left to right. And you get this sort of effect, orange effect. Now, in dealing with anti-aliasing on this problem here, if you do area sampling or area edging on this, what you're doing is not calculating the intensities and averaging them down. What you're doing is smoothing the surface out where it gets really puckered together, which is better than doing nothing, but it's really not the right thing. Doing the right thing is more gross than I want to even think about. But this is the thing with area averaging. You can see, especially around the North Pole here, it looks smoother than doing the point sampling of the image.
Did you start with a picture of an orange?
No, I just started with trying to draw like the wrinkles in my hand, basically, and I just happened to put it on a sphere because it was a handy object I had laying around, and put an orange map in there. It looks like an orange.
Navel on it.
This was an early attempt to put sun-kissed on. This again shows sometimes the bookkeeping problems of this. The replication factor was different for the pattern that was used with sun-kissed and the rest of the orange. This is what it's supposed to look like.
Sort of. You can still see the breaks.
Yeah, there's a funny little sort of seam here and there. And so forth. Why don't we just show the film right now rather than go through much more of the slides. The film shows some of these things moving around. Unfortunately, the AV guy, I think, has to leave before too long. Can you make that not jump around? This particular film is kind of old, and so it's maybe a bit hard to thread. Now, this particular trick works well for still frames, but the proof of the pudding is whether it works for movies. This is just random intensity pattern on a kind of rotating patch. Little flapping back and forth effect is, again, mistakes in the algorithm where it's not calculating, it's, again, doing the linear interpolation. And this is the wrinkles. And the idea is, does this look like real wrinkles as the thing rotates around? And it's still a fairly convincing image. The wobbling is kind of distracting, unfortunately. But this is meant to show that where the mathematics works, something that looks like bumps on one side, the light's coming from the upper right-hand part, look like dents on the other side. Comes out, right? Yeah. Now this is a hand-drawn little pretzel-shaped thing with some random noise, essentially fractal noise added in the background to make it other than perfectly smooth. Looks sort of like construction paper, maybe. Same sort of thing applied to a sphere.
They seem to be flattened down as it goes toward the edge, though.
Yeah, there's no alteration of the silhouette outline at all, because it's still a perfectly smooth sphere. We're just playing games with the calculation of the intensity. Here's a armor-plated strawberry. The thing in the background was just what happened to be in the frame buffer when I started running this thing, so I just left it there. And this is sort of to show what happens when you stretch the thing out. The bumps kind of flatten out in the X direction, even though they stay bumpy in the Y direction. This is a very early attempt to make, this is just intensity mapping for globe of the Earth. This is not bump mapping.
What drugs were you on when you were making this?
Purely electronic drugs. Here's a donut with a map of the Earth mapped onto it. You can see the highlights on here are not dithered. There's no dithering done in this. You can see a lot of quantization thing in the highlights, but it's not too lucid. This is an actual almost scientific application of this. This is a map of the surface of Venus as it would look like without any clouds. The Pioneer Venus orbiter has been going around Venus taking altitude measurements with a radar altimeter. Sends down a radar pulse, goes through the clouds, bounces off the ground, and they measure the time it takes to get back so they can find out how far the surface is below the probe. They've been building up a database of the altitude of this thing as a function of latitude and longitude, just a bunch of numbers. But the altitude is a function of two parametric lines are exactly what the program needs, and so I filled that into the program and made this picture. The altitude is represented both as the wrinkles on the surface, and also the color codes are altitudes as well. So you're seeing the altitude represented two different ways.
What's the problem with performance?
There's missing data there. That's where the probe didn't go over, right? It's going over in a orbit something like this, and as the Venus rotates underneath it, it gets all that data except for what's going on with the poles. And so they've actually got names for most of these mountains and so forth now, but that's about the resolution that it's at. Okay, that's it.